Alright, hello guys, and welcome back to Engineering Principles Advanced on Learn.io. Today we're going to be talking about IMA, AMA, and efficiency. So if you don't already know what mechanical advantage is, I do recommend going and watching the first Engineering Principles course, where we cover mechanical advantage and just some of the basics of it before coming back to this. So let's jump right into it. Ideal mechanical advantage, or IMA, is a theoretical mechanical advantage that you can get from a machine. And to calculate this, we use the equation IMA equals dE over dR, which basically means that the ideal mechanical advantage that you can get from a machine is equal to the distance that the effort force travels divided by the distance that the resistance force travels. And I'll explain that in a little more detail in just a moment. So for actual mechanical advantage, we're using the equation AMA equals FR over FE. You'll notice we're actually using the forces this time. The resistance force divided by the effort force. This is because some of this force is lost to friction. Because of that, our IMA is not always the same as our AMA. And we'll see that in just a moment when we look at this example. So the efficiency is how much of the theoretical MA or the IMA is maintained as AMA. And it's calculated by dividing the actual mechanical advantage by the ideal mechanical advantage. Again, this is because no machine is completely efficient. Your ideal mechanical advantage will almost never be your actual mechanical advantage. Actually, it never will be, because you're always going to be losing some of the effort that you put in to friction, to air resistance, and to other such forces. So with all of that said, let's hop into an example to understand these equations just a little bit better. So here we have a lever with 5 newtons being applied 1 meter away on the left and 3 newtons being applied 2 meters away on the right. And the problem is basically asking us to find the IMA, AMA, and efficiency if the effort force is 3 newtons. All right, so let's see. Our IMA, in this instance, is dE over dR, so the distance that the effort force has to travel. In the case of a lever, that's the distance from this 3 Newton force over here right to the center of the lever, so 2 meters. In the case of an inclined plane, the effort force has to travel the entire length of the ramp. Then we have the dr, the resistance force's distance, the distance resistance. That would be, in this case, the 1 meter, the distance that this force has to travel right to the center, 1 meter. In the case of an inclined plane, for example, that would only be the y value of the ramp, so just directly up. But in this case, we have a dE of 2 meters divided by a dr of 1 meter, which gives us an IMA, be nice if I had the I, IMA of 2 to 1, or you could just write it as an IMA of 2. You'll notice that it's unitless because IMA and AMA both represent ratios. They don't have units. Moving on, we can calculate the AMA since we have both the forces listed. Here we have a force resistance. Notice this time that the resistance is on top, whereas in the IMA calculation, the effort was on top. It's a little confusing at first, but it is a very important thing to keep in mind and to remember when you're doing these problems. So our resistance force here is 5 newtons. So we have 5 newtons, 5 newtons, and we divide that by our effort force of 3 newtons, which gives us an AMA of 5 divided by 3, that should be 1.666, repeating, which I'll round to 1.67. So that leaves us with the efficiency. The efficiency of a machine is calculated by taking the AMA and dividing it by the IMA. Our AMA in this situation is 2, our IMA is 1.67, and that gives us an efficiency, I believe, of 0.835. However, efficiency is always measured in percent, so we just multiply that answer by 100 to get our final efficiency. Efficiency equals 83.5%. Again, notice it's never going to be 100% since you're always going to be losing part of your mechanical advantage to frictional forces. Now, there are two exceptions to this equation, although one of them is kind of like a half exception. The first exception is for pulleys. When you're doing pulleys, for pulley IMA, we want to just use the system that we were using in the last course, where we just count the number of strands that oppose the load we're lifting. If you don't know what I mean by that, I recommend going back to the engineering principles video where we covered levers, wheels and axles, and pulleys, because I go over this method in that video. So screw IMA is also dE over dr. However, since screws actually convert rotational motion into linear motion, it's easier to think of it as 2 pi r over p, where p is the pitch of the screw, which is not threads per inch. I don't know why that's written here. It should be the distance between threads. So the other way around, it's inches per thread. Keep in mind that screw specifications are always in inches, so the radius that you calculate also has to be in inches when you're calculating circumference. If you're given a radius in centimeters or meters, you will have to convert it. So with all that in mind, let's look at a problem for screws. Here it says that if an 8-inch long wrench rotates this screw right above, it's asking us what the IMA is. So first thing, just looking at the screw, it is 1 inch tall and has 10 threads. So I've actually drawn small black curved lines over each thread. Each of these little curved things is a thread. So the distance between those is what we need to find for the pitch. Well, if the screw is 1 inch tall and it has 10 threads in 1 inch, that means the distance between each thread has to be 1/10 of an inch. So P equals 1/10 inches. From there, we just need to find R and then solve the equation. So what's the radius in this case? Well, you'd assume that we don't actually have it since we don't have the radius of the top of this screw. But we're not actually applying the force at the end of the screw. We're applying the force at the end of the wrench. Because of that, the radius and the circumference actually becomes the radius and the circumference of the end of the wrench. So our R, let's keep that small r, is 8 inches. So with all of that, then we can solve this equation where we have 2 pi, I'll just write pi in letters, 8 inches divided by 1/10 inches. The inches cancel out, and we can solve this to get an IMA of, let me plug this in real fast, 2 pi times 8 over 1/10 gives us 502.65. This seems like a really, really large number though, doesn't it? And that's because screws actually have the largest IMA of any machine. Unless you get really intense with your pulleys, really long with your levers, and like unrealistic with your ramps, screws tend to have the highest IMA. The issue is, because they're always in such tight contact with the walls that surround them, they also have by far the lowest efficiency of any simple machine. Because of this, their AMA ends up actually being relatively realistic. So a machine with, 502 as its IMA might end up with an AMA somewhere between 1 and 4. It really loses a lot in its efficiency. But yeah, hopefully that helps you guys understand IMA, AMA, and efficiency a little better, just the differences between them and how to calculate them. Thank you very much.